All right, guys, let's get started. It's 2 o'clock. All right, guys, so let's get started. A few announcements. So we're currently on week 11. That means next week is week 12, and we have exam 2. Okay, so make sure to prepare for that. Similar to exam 1, it'll written exam like that online. You need to come to class. It's closed notes, but you're allowed your cheat sheet, right? And you can write whatever you want on it. It's comprehensive, so it's going to cover anything from like the beginning of the semester up until what we cover on Wednesday. Okay? All right. Any questions about the exam? All right, good. So that's one important thing. We're getting close to the end of the semester. We have about 6 weeks. Okay, so keep that in mind. We're going to have, we're continuing neural networks, but we are switching to PyTorch today, right? So this is like the state of the art. This is where you get to use GPUs and all of that. And I still have a lot of individual topics that I also want to cover here and there, right? But really the one common theme will be PyTorch going forward. Okay, so today we'll start with Iris again, use very basic stuff so you guys learn how to know how to code it. It's very consistent with NumPy, so a lot of it is going to be very familiar. So we're going to build a deep neural network first. You'll have a homework assignment. A lot of the things we're going to do for the rest of the semester is going to revolve around images. So we're going to do. Here, let me. Okay, so we're sharing again. Yeah, what I was saying is the focus is on images. So there will be a homework assignment using the MNIST dataset to building a deep neural network and measuring performance. Then we remember we are going to have 2 competitions. And so, I haven't decided on the dataset yet, but the 2 competitions, essentially you build a model to classify images, okay? These are going to be color images, and it's going to be phase 1 and phase 2. Phase 1, you'll implement it from scratch with something called a CNN, and you can go, as long as you're implementing from scratch, you can do whatever you want to win the competition, okay? So that's the whole point, right? The whole point is that you will do everything that you can to build the best model, right? Obviously, it's going to be a large data set. You'll need to use GPUs, so it's going to have all the elements, right? And then after that, phase 2, I will it'll be the same thing, but you can use something called transfer learning. And so we'll talk about yes. Just a 3D printed trophy of the university. 3D printed little, just not even that big. I think, yeah, it could be like that. Could be. Maybe. No, it's just the lion of the university.
Okay, because we actually have that in the CSC, but it's called the one in the School of Johnson.
Well, there will be 2 trophies because there's 2 phases. There's phase 1 and phase 2. So, but yeah. So the thing is supposed to be fun. That for sure, I can tell you. And it gives you a lot of chance to try lots of things. Use Colab, use GPUs. You will learn what transfer learning is because you will be using it to try to win, right? And I'll say this right now. So transfer learning is essentially when you use weights that someone else produced, right? So a model has been pre-trained by someone else. You take those weights and you start with them, but then you fine-tune with your own data, okay? So whereas in phase 1, you can't do that. You have to start with weights that are random. So you do all your training. Do you guys understand the difference? So that's going to be essentially phase 1 and phase 2. All right. So, and it all involves PyTorch. It'll be the same coding pipeline that we're starting today. Okay, so that's essentially how it's going to work. But yeah, so that's the plan. And then along, during those topics, every now and then I'll find some room to put in maybe a decision tree or SVM or a kernel, just some additional ideas that I want to cover. Okay, last year I used Scifar 10. I'm not sure I'll use that same data set this year, so I'll think of something else, but it'll most likely be an image-based model. So you'll learn that you can use things like pre-trained ResNets and so on. Obviously, these models are massive. So then you're going to start facing the challenges of the modern era of AI, which is that you just don't have enough resources, not enough GPUs, not enough memory, etc. Do you see that? So you'll face that kind of a challenge. So you'll definitely, whoever has the most GPUs, the most time, the most data, usually will win the best model. Okay. But yeah, so anyway, so that's the plan going forward. So today we're starting with PyTorch. We'll start with something familiar, the Iris data set, and you'll just learn the basic approach, building classes, etc. So you guys are section 1. Whoops, not there, not there. Let's go to the little hint. Yeah, section 1, so let's go here. Okay, so we should be, and the perceptron, we've done that. This homework is due, it'll be available until March. Yeah, it's due March 25th, right? So this is the homework you guys are working on, deploying, and all that. So this one, I haven't seen that many submitted. All right, and here we are, the classic Iris torch to motivate NNs. So we started with the perceptron. That's a neural network. We've talked about a lot of those ideas. We still need to address some of those, but in the interest of time, I have to start the torch sequence, and then I can continue, diving into all the details, right, of stochastic gradient descent and everything like that. But today we need to get going on this one. So let's take a look at a few things that I have here. I have some notes, so I can click on this, right? And essentially, this is what you should read. This blog post, chapter 4, getting started with deep learning. So these are my notes, pretty much very detailed. Everything that I'm going to, all the code is explained in great detail. So go ahead and read through that, okay? And today I will implement, our first example of this. Oh, and we're building neural networks just like before, but just keep in mind this time around you're building professional level. So this is the language that you would use, at work, right? So you would use PyTorch, right? Or you would use the transfer learning ideas that we're going to explore, like ResNet, etc. Okay, so that's essentially what we're doing. So please read through this. Definitely, this is your reading assignment for the next few weeks. Become familiar with everything here. All right, now we can go to the code. So let's go back to the table of contents. Table of contents here. Okay. And so we're here. Now let's click on repo torch. Okay, and this is the course, like those notes, right? Chapter 4, this is the code itself, right? So this is what you need to master. If there's one thing you should get out of this class, is this code. Do you see what I'm saying? This is like essentially the most important, the key, the basis for everything else going forward. And from this code, you can just add more to it. Keep adding things and make it more robust, etc. All right, so I have a few examples here. I have the wine quality data set, and I have the Iris data set. we'll start with Iris. It's our most familiar data set. And we're just going to build a very simple classifier. Then we're going to go and look at how we can, build a regression model, what's the differences, etc. Okay? So we can start with this Jupyter Notebook, classification. And keep in mind, we've been talking about neural networks, but you're actually very close at this point to building a deep learning model, right? So deep learning is just a neural network that's deeper. It has more layers, right? And so that's what probably by today or maybe next week, you'll be implementing a deep learning model. So you've heard of deep learning, hopefully, and that's, one of the key concepts. That's what ChatGPT is, right? So it's a deep learning model built on the architecture, a more advanced algorithm called a transformer, but it's built on top of all these ideas. All right, so let's go ahead and think about this one. So we want to bring in the Iris data set as a CSV, so I probably already have this. So let's go to Colab. And yeah, today we're just gonna, this week I wanna really just spend all the time getting the code running, giving this to you, as I want you to start working on the competition as soon as possible. All right, let's take a look at let's connect to Google Drive, and we should have in there my drive. So Iris, here it is, Iris CSV, so we already have it, so we're just going to copy the path. Again, I'll remind you, if you don't remember, I'm sure I said this at the beginning of the semester, because now it's going to become relevant. Your next homework assignment, you have to train a neural network, a deep neural network probably, to classify images. You'll need a GPU. That's the reality of it, right? So now it starts to get, you need a lot of memory. The architectures are going to be very deep. So you're going to have to start using a GPU. So the way that you do that is you click on Runtime, change Runtime Type, and essentially here you select GPU. Do you guys see that? And that's it. So T4 GPU, for instance, you'll see that if you run with the GPU instead of the CPU, it runs much faster. The beauty of this code, PyTorch, is that the way that it's written is that you're creating in memory what is called a computational graph of just operations and data. And that graph that you're creating is independent of whether you're using a CPU or a GPU in the background. Do you guys see that? So that's what's really nice about this. In the past, around 2014, if you wanted to use a GPU, you had to code for a GPU. It's different, right? You're programming in parallel. It's just a different thing. But when a library like PyTorch was created, it was created so that you didn't have to learn a new way of coding in parallel, right? So that's a valuable skill to have, without a doubt. But if you want to, but it's got a very long learning curve, right? You have to program in C. It's quite complicated. So this approach of using libraries like PyTorch and TensorFlow really gets you there, quickly. So we program for either CPU or GPU the same way. All right, so I'll stay with CPU because nothing I'm doing right now requires GPU, but once you start using images, it explodes. You use deeper neural networks, it explodes. You use CNNs, it explodes, right? So that's what we're going to see in the coming days. All right, so let's get started here. I'm going to have the path to my file, Iris, just to be something that is familiar. Let's go ahead and add a few libraries, and I may need to install some of these as well. So let's go, but as you will see, a lot of these are still the same libraries, NumPy. Notice that now I'm adding this library, Torch. Do you guys see that? That's it. This is the really important library that I'm adding right now. There's two powerful frameworks in this area of deep learning. One is called TensorFlow. I'm sure you guys have heard of it. That is from Google. And then there's this other one called Torch, PyTorch. This one was developed at Meta, Facebook. So as you might imagine, one big company doesn't want to use the tech of the other company. They want to be independent. I've used both in the past, and I started with TensorFlow and I switched to Torch. So that tells you something important, right? And a lot of people have done that. It is just a very nice language. Definitely easier to understand. We're going to use pandas, sklearn, same ideas. And then notice now, we were going to have these three functions here in Torch. So whenever we're creating a neural network, we're going to use this construct from torch.nn, right? And we're going to call it just nn. So this allows us to create our neural networks going forward in the code. And you'll see I'm going to take, for an object-oriented approach, we're going to use something called class inheritance, which I'm sure you guys have covered in your object-oriented classes. Maybe you saw it once and you're like, I will never use this, right? And actually, this is a very nice way of coding neural networks because you're building on a neural networks class and you're just adding to it, right? So you're reusing a lot of the ideas already built in. So this will be, and what's great about this is you can build ChatGPT with this same approach, right? So it just gets a little bit more complex. But yeah, so torch NN and then torch optim, we're going to learn, like we had the update rule and the perceptron, right? You guys remember that we had that, we were doing in a loop, we were updating the weights, and we had that update that we arrived to. We derived that. So we're going to need now something called an optimizer. And this is what is essentially doing that update for us, but we just have to get used to the way it is done, right? And what it's doing in the background is extremely powerful. This is the reason why we can't use NumPy. Okay, so we need something extremely powerful like this to be able to solve neural networks, right? To use these algorithms called stochastic gradient descent to update the weights. Right, and the two libraries that I mentioned, TensorFlow or Torch, have this construct for us. Right, this it's a solver if you want to call it that, or the way that we optimize things. And then this one, Torch NN functional, is where we just bring in functions that we use to train our models, as we will learn. MSE, for instance, mean squared error, will be one. And please, as I said, read that link that I gave you. It's got a lot of details, okay? Lots of details, lots of concepts that are thoroughly explained, okay? So that's your reading. All right, so we added a few libraries here. And let's go ahead now and add a few more. And some of these are just for plotting things nicely. Matplotlib, of course, that you're familiar, MLextend for plotting heat maps, etc. We may need to install this one. Our familiar train test split, notice that even though you could just use PyTorch functions, I sometimes just like to use the things that I'm used to. So I'll start with pandas, convert something to NumPy, do processing in NumPy because I know already a lot of code, and then once I'm done, you will have to change things to Torch. So this is going to become an important concept, right? You're building neural networks in a computational graph. This is a PyTorch computational graph. So you cannot add NumPy arrays to that. They have to be, the data is the same, but the data structure has to be compatible. So everything that you add to that in Torch has to first be converted into a Torch tensor, okay? And that's a good thing that you do explicitly. Make sure that you're doing. All right, but there are steps where you can still use sklearn, etc. We will also use these two constructs called tensor dataset and data loader. These are really great because they allow you to essentially put your data in a specific format that PyTorch likes. So all we have to do is kind of get used to the approach, of how we take our data, format it, and then it'll fit nicely into these constructs, and then it just makes once you start implementing your code, right, you get to do a lot of things with like 2-3 lines of code, versus if you were doing everything from scratch, it'd be 20 or 25, and it would just make the code, harder to read. So essentially, this is very streamlined. But also, another important thing is all these objects are built, anything related to Torch is built to be fast, really fast. And this is key. And this is why I do the competition in this class, because the point is to win, you think, oh, I have the weekend to work on this, and then you get bogged down in, things just being very slow, and you start actually trying to find efficiencies. How do I make this faster? What do I do? So things like that. Fewer iterations, but then there's a cost to that, right? So you'll have to play with all those concepts, which is the very reality of machine learning today, right? All the variables. So let's go ahead. I believe one of these will fail. I didn't, I guess. If it does fail for you guys, if you're following along, just make sure to run pip install on that ML extend. Okay, the pip install command should be here. All right, we don't need Onyx here, but as I've given you already, right, one homework assignment where you guys deployed, to JavaScript, right, very easy one, the perceptron that you're still working on. At some point later in the semester, we'll cover Onyx, very easy, super easy, in fact. You create a neural network, and guess what? You can save it as a file and then build a website. Right? You guys maybe are building websites for different kinds of things, and you want to have a little bit of machine learning in it. So boom, you can have your model there running, doing predictions for you. All right, so we'll cover that, but that's not the focus of today. The focus of today is just to get the very basic PyTorch pipeline going. Okay, and then I haven't introduced it here, but just to give you a heads up, there's something called the torch.hub, something like that. And this is one of the ways, a library and set of modules that will allow you to get pre-trained models, right? So as we're going to be adding this concept of transfer learning into this course coming soon, for phase 2 of the competition, you will need to decide, okay, what do I do? You'll have to make decisions like, well, I can use a ResNet 16, but my friend over here is using a ResNet 50. But why is my ResNet 16 not performing as well? Do I need to use the ResNet 50? And if you use the ResNet 50, oh, but I don't have enough GPU. What GPU are you using? And you see that, and you start in this whole thing of trying to win based on algorithm, resources, data, and time. Okay, so like I said, I'm still working on the data set, trying to figure out a new challenge this year. So I'll probably announce that next week. But we're in good time. And then you can start working on phase 1 and phase 2 of both these challenges. So we did this one. So we have the libraries. These went through. XGBoost, we don't need that here, but we'll cover it at some point as time permits. When I cover decision trees, probably, as it is a decision tree. I always make a point of mentioning XGBoost because we all think, okay, neural network, deep learning, the best probably. But as it turns out, there is one algorithm, the XGBoost algorithm, which is not a neural network, is based on decision trees, and that is always a really good algorithm to have available. A good model is extremely powerful, and it defeats a lot of neural networks sometimes when you're dealing with small data sets and regression type data sets. But so I always emphasize that one in particular. All right, so we have our libraries for sklearn. For metrics, remember this is iris classification. These are the Onyx files. I don't need them right now, but I guess I'll run them just to make sure that they will run. Okay, so this one does require Onyx runtime for me to install. So I'll skip it for now, because I do not need it. Okay, and then we'll start looking. All right, and here we are. So we're going to build our first neural network in PyTorch. Okay, so here actually I can show you several algorithms, right? So I could show you logistic regression, I can show you multi-layer perceptron, I can show you a deep learning algorithm, and they're all very, very similar. I just have to make like a tweak here and there, and boom, I have now this algorithm or that algorithm. All right, this is a linear versus a nonlinear, and so all these ideas are all actually the same exact approach, just the architecture gets more complicated. So there's going to be certainly a lot of new terms probably, but you're gonna get used to these by the end of the semester because they become repetitive, right? So today you're just getting all of them, and then essentially as we move on, every week maybe there's 2 or 3 new ones. So lots of things to consider here. Number of epochs, right? Number of epochs, that's the term that we use for the number of iterations. So as you saw in the perceptron, we just said we're gonna repeat, right, and update the weights 1,000 times. So this is a parameter that you set, and this is 4,000. We have this idea of the learning rate. We still need to dig into that, but essentially now this is essentially in the update, right? It is by how much you're adding or subtracting from the weights. That's essentially the idea. Do you guys see that? So it's a little value that you can change and play with, and it's actually really important. Usually the default value is about that, 0.001. But some problems need it to be 0.01, right? And other problems might need it to be 0.0001, right? So it's just something that you play with, called a learning rate, and we will see this later. We have this idea of batch size 16. What is this? This is actually really important. So you're used to maybe, and that's how we did it with a perceptron. Imagine we were training a model. We would give it one image, train, give it another image, train, give it another image, train. But what if you have 1 billion images? That's kind of slow, right? Wouldn't it be nice if we had some other way of doing that? Plus, let's say that you decide, okay, I'm going to use a GPU. Well, a GPU does things in parallel, right? So if you give it one image, essentially the GPU is underutilized, right? So you have all this room and it's empty, right? It's because you can fill it up with data. And so that's why we have this thing called the batch size. This is an important parameter that you can play with, but essentially it means that instead of giving it one image at a time, we're going to give it 16 images at a time. Do you guys see that? And they're going to be operated on independently, right? But all 16 will be used to update the weights of the model efficiently. So all of this is like baked into the approach, right? So it has been done this way to be efficient. So the batch size, has limits because the GPU will have limits in memory. If you were training like a transformer, a chat GPT, right? Something larger than 64, it starts to get, you start to essentially run out of memory. Okay? You'll see this with the challenge and even with the MNIST data set. Maybe you want to finish training faster. You set it to 512 and it'll just run out of memory. So then what do you have to do? You have to scale down. Notice that you will want these to be multiples of 8 because the architectures are built that way, right? So 8, 16, 32, 64, and so on, okay? So this is something called a batch size, but in essence, we need to give the data 16 samples at a time. So that, of course, imagine if you were coding that from scratch. Let's say that I asked you, if we had the time, right? That could have been a nice homework. Create the code for reading batches from scratch. That's involved, right? You have to go in, you have to slice 16 things from the code, and then with an index move to the next, and so on. But because of several techniques that we're going to use, actually, in tensor data and tensor, these two, tensor dataset and data loader, it'll be, as long as you put the data in the specific format, it'll be very easy to load the data into these objects, and then these objects already have that built in, right? So that you can read the data in batches. So we will see that as well. All right, so pretty important concepts, and as you can see, a lot of our coding discussion now revolves around this idea that we want to be fast, do things in parallel, because we're anticipating that we may need to use the GPU. That's essentially the trick. Okay? So now let's go ahead and read in the iris dataset. So I'm going to use pandas. I like to use pandas when I read in data. Let me just change the path here. Okay, and let's run it. Okay, so that ran. Let's take a look at my data. Okay, and perfect. As you can see, everything is good here. You know, I like to use iris for a lot of the things that we do because it's familiar to us, and so we know quickly what we're seeing. 150 rows, 5 columns, sepal length, sepal width, petal width, and then the species Setosa, Virginica, and Versicolor, 3 classes. Just like with NumPy here, PyTorch cannot use the words, right? So we'll have to change that to numbers. Okay, so we'll do that in a second. So we printed that. So here you can see I'm going to create a map essentially so that we can encode the each word Setosa, Virginica, Versicolor into specific numbers 0, 1, and 2. Okay, so I'm going to create this. Notice pandas actually can help me do this. So from iris raw data, which is this pandas data frame, I grab the species column. You see that here, species column, right? And then I'm going to map so that whenever it sees the word Setosa, it now just replaces the column with 0, Virginica is a 1, and Versicolor is a 2. Okay, so that's done. Okay, so let's go ahead and run this one. And as you can see, same data, but now the column for the labels is no longer words, it is just the numbers, 0, 1, and 2. Any questions on that one, guys? All right, so very easy to do. In the past, we have done this with the label encoder, but this is another way of doing things, as pandas is very powerful. All right, so now let's take a look at the labels that we have. The labels that we have. So we have sepal length, sepal width, petal width, and species, right? One thing that, you know, in data science that you always want to do is look at your features somehow. So this is totally independent of a model, right? We're just going to quickly take a look at the correlation coefficients. Essentially, it tells you how variables are correlated to each other. So you can see that there. You can see essentially I'm comparing, you know, the variables to every other variable, right? So for instance here, we're comparing the label species to sepal length, sepal width, petal width, and species. So obviously species to species is 100% correlated, so 1. Notice that this one is negatively correlated, right, to the labels. So that tells you something, right? So as something goes up, the other thing goes down in the values, right? This is better used sometimes with regression problems, not so much with classification, but still is a nice tool to have. Okay? Any questions on this one, guys? Just to visualize the relation between the variables. All right, so now we obviously our data is in a pandas data frame. So we want to convert it into a NumPy array, right? So notice this is usually the pipeline that I follow. There's a lot of code, a lot of examples, a lot of features that you can still do in NumPy, and so it's a nice thing to go to from pandas to NumPy. Then maybe you do some processing of the data in NumPy, and then once you're done with that, you switch over to PyTorch. You know, that's a nice thing to do. So here, notice I'm taking the pandas data frame and I'm just converting it to NumPy. I like to add like underscore NP at the end just to know that that's a NumPy. It's just for me to know what I've done with the data. And now you can see I can print it again just to look at it. This is now a NumPy array of the 4 features and each of the labels, okay, that we're going to define. Let's add a few more labels here. Okay, so now that that's done, we always want to print the shapes. Okay, so we want to print the shapes. So we can see it's 150, 4. Obviously, we need to break this up into X and Y now, right? So we need our X data and our Y labels. And so we're just going to use slicing for that. So that's a concept that we've been covering since the beginning of the semester. Okay, so here I'm going to create X first. So notice here, slicing, this should be something you've mastered by now, right? All the rows. And from the columns, we grab all of them except for the last one. All right, so now if I print x.shape, that is 150, 4, right? So it's just missing the labels in the last column, so I need to slice those out. That's going to be my y. Whoops. You can see that there, so we grab all the rows, okay? And then we just grab the last column here. Okay, so that's going to be my y. We can print y here. And there it is. Those are my labels, 2s, 1s, and 0s. Yep, 0s are there. So I have all the labels, and I've created my x and y. The next thing now will be we want to convert the data. If you notice, the data is floats. So this is a classification problem, so they just need to be integers. So let's get rid of that dot, and that's just typecasting it to int. Okay, so if we do that, you can see they are now integers instead. Okay. All right. Now, one thing that I like to do, that Weka, for instance, did this for us, is we could see the data distribution. So you always want to see, for any problem, the class distribution. So you know if it's a balanced or imbalanced data set. So this is one way that you can do this. You essentially look at the unique values first, call it the set in Y. So that's going to be 0, 1, and 2. So there's 3 classes. Okay. And then we're going to, we can take the length of it, which is 3. Okay, and then we can plot a histogram. Here, a histogram of y, just using this simple code. And this will show us that essentially there's 3 classes, 0, 1, and 2. And each one has about 50 samples, which is something that we know from the iris data set. So that essentially the data set is now balanced. We know it's balanced, so that is good for our classification. So this semester, for instance, I haven't decided, right? Cypher 10 is a balanced data set. But I could decide that I want an imbalanced data set, right? And so that would present different challenges for you for the competition. So we'll see what we end up using. All right, so now that I have this, we want to split the data, right? So we're going to do the split. I'm going to do the split randomly. So remember here that we provide a seed for the split. If I just give it a number like 42, then it's always going to be the same randomization, always. However, we talked about tenfold cross-validation, right? But that code is kind of complicated to implement. So an easier thing is just to have something like this, a random seed. That way, all you have to do is run your Jupyter 10 times, look at the performance, because it's randomizing every time, right? And then you'll see a tendency. right? Because it's going to be different one. So that's like the poor person's tenfold cross-validation without having to implement a whole bunch of fancy code. That's, you know, what I like to use and to keep things simple. Okay? So we'll create the random seed here. And now our familiar train test split for breaking the data into X train, Y train, X test, Y test. So you can see that, the exact same thing. We give X and Y. We're going to do a split of 20% for testing, 80% for training. Notice the random seed that I just calculated, and then it gives me my X train, X test, Y train, Y test. Okay, so there it is. Okay, nicely done. We can print the shapes now. All right, so we're printing the shapes of each one, and you can see they are 120, 4, 30, 4, 120, 1, 30, 1, right? So train and test. All right, so a lot of this is familiar to you, as this is something that we've been doing all semester. But now we're starting to switch over to Torch, okay? So there's a couple of things that we're going to do. One of the things is check the data type. So the data type is float 64. That means, you know, you're allocating a lot of RAM, a lot of space for these variables, float 64. As the models become big with images, you know, and you have a lot of layers, etc., you're going to be using up a lot of memory, right? Might create errors. So one good suggestion is to change the data type to something like float 32. Okay, so we can do that here, for instance. Notice that I'm going to leave the y as int 64. That's fine, but although you could change it if you'd like. But notice that we are changing to float 32. So essentially smaller. Okay, so X train Y test, and now we can print the data type again. And guess what? They are now float 32. Some people, when they're building applications, you know, let's say you're building something on a Raspberry Pi or, you know, something more embedded, they can actually make the neural network be, you know, float 16 or float 8, right? So maybe that is still accurate enough for you to deploy the model. Do you guys see that? So these are the tricks as you start to use these very large models that you have to start considering, okay? And this is a very real situation going on in the world of AI today. All right, but here, as you can see, we made this smaller to float 32. And this is confirmed. All right. So now comes the part that's new. We are now, of course, we can't use our NumPy arrays, right, in Torch. So we have to convert them to, so from NumPy, we convert them to Torch. So notice we're going to grab all of them, X train, X test, Y train, Y test, and then from NumPy, we're going to essentially convert them into Torch tensors. Do you guys see that? So it's still the same data. It's just going to be a different underlying data structure. Okay? So that's the idea. All right? Other things that you need to do, the data, it's always recommended that you normalize it. Machine learning models like normalized data or standardized data. So scale the data, basically. And we've talked about this before. You know, let's say that you have one dominant class that goes from 0 to 100,000, and another class goes from 0 to 1,000, so you have different scales there. You really want things to be in the same scale. Okay, so this is one way of doing it. For now, we're just going to calculate the means and the standard deviations of these. Okay, so how does this work exactly? So you're going to take, let's go back to the data over here that we printed. So I'm going to take the mean of these, right? So I know that this is 150 by 5. So when I take the mean of all this data, I'm going to end up with just one vector that is 1 by 5. So that means that I'm going to look at all the values in the first column, and I'm going to take the mean of it. So if I look at these numbers here, right, what would be the mean of these numbers, of this first column? Looks like maybe 6, right? So it looks like a 6. Now if I look at the second column over here, what would you say is the mean of all those? 2.6 maybe, right? So you can see that we create one single vector of just the means. We look at this one, seems to be around 4. This one would be about 1.2, etc. So we're taking the means across each column. So that's what we're doing, and that's something that we're going to use later on to normalize the data. Okay? So you can see here then, that's why, so here we use X-train TR, and we calculate the mean and the standard deviation of these, okay, across the 0 dimension, which is across all the rows. So now I compute these X means and X deviations, and let's actually take a look at them. X means, and there they are. So it was actually 581, 305, 36, and 116. Do you guys see that? This is extremely important. You know, if you want to win the competition, normalize your data. In fact, you're going to learn that you should normalize even the data between layers in the neural network and so on. So these are the little tricks that make the difference, okay? And we could also print X deviations if we would like as well. And this just gives us the mean and the range of each value there, right? So up and down. So like we have a little range of the features. So this data we will use later to calculate, to normalize the data. But normalizing the data, it's going to be something like X minus mean, and this is all divided by the standard deviation. Let's call it sigma, right? And so that's essentially what's going to happen. So right now, you already calculated the means, right? X means. So that's this one. And then you calculated the X deviations. That's this sigma. So then when you have each of our samples, we just normalize it. Do you see that? And that value is now going to be in a nice scale from between like -5 and +5. And so instead of being 100,000 one direction, 0 to 7 another direction. Do you guys see that? So it, you know, and we address the scaling issue. I'll repeat, neural networks really like scaled data to learn correctly. So we've computed these so far, okay? And later on I will show you how you can actually put those in the neural network itself and do the computation there. All right, so we print it. So, all right, so we're ready now to start. A lot of the, you know, we've processed the data. We have everything that we need. So the first thing we want to do is we want to learn how to load our data into the Torch data loader, okay? This is, I highly recommend that you do this. Before these existed, you had to do all this manually, and it was, you know, hard. Keep in mind, you know, as you get new data sets for the homework, etc., this will be one of the most challenging parts, right? Loading the data into a data loader. But if you follow this approach, it should be pretty easy and straightforward. So how do we do it? So let's create our data loader. The first thing we want to do is look at how many samples we have in the train set. So X-train has 120 samples, okay? Good. So now, notice what I'm going to do here. I'm going to do a list comprehension. I'm going to do a list comprehension. And essentially, it's just a for loop, right? So you can see it here. for I in range x train shape. So x train shape 0 is 120. So I'm going to iterate from 0 to 120. Right? And I'm saving the values in I. And then notice that I'm going to create a list of tuples. Okay? So the list is the square brackets, but the objects in the list are going to be these tuples. What's a tuple? This object here. If you notice, I'm going to move it down just to describe it because, it's like that. If you notice, this is a tuple. It's essentially just two items inside these parentheses. Do you see that? So a tuple is, in Python, something that looks like that. This could be like A, this could be B, okay? That's a tuple. So we are creating, essentially then, a list of tuples with our data. And if we put the data in this specific format, then it'll load nicely into our data loader, okay? That's the trick. So this, I'm building this object, and then this object should load nicely into the data loader. All right, so if you understand that, that's key. You just then have to think of your data and how do you put it in that. All right, so now that you understand this, we also need to understand the format of A and B, right? So A and B need to be in a specific format, so that's what we're going to look at here. All right, so notice this is A and this is B. Okay? So what we do is from x train TR, from the torch tensor, we just grab I. Do you see that? So essentially what we're doing is we're just grabbing every row in the torch tensor that contains x, contains the x data. Remember that these are vectors of 4, right? So if I come here and I print x train TR, notice it's these vectors, right? So when I have index 0, I grab just that one. But that's a torch tensor. It's a vector, okay? That's key. If it's not in that format, it's going to break. When index is 1, then I grab that one. When index is 2, I grab this one. When index is 3, I grab that one, and so on. So I'm iterating through all of them, and I am loading here vectors of 4. Do you guys see that? And that's my A in the tuple. B is going to be what? The associated label, right? But we already have those. We know that if we have x train TR, which is 120, 4, then we also have y train TR, which is 120, 1. So we just have to grab the corresponding label given the I. So I have I and I have I, so they just have to match. Do you guys see that? That's the key. But don't load it as a tensor here. Make sure that you do this dot item because it's going to be expecting a vector, a torch vector, and just a value, a number. Do you guys see that? So this is pretty important. So if you put your data in this format, then everything else should work. Okay? So let's try it out. Okay, so it ran. Now if we print this, it's going to be somewhat big. You can see what I was saying, right? So it's a list where I have a torch tensor, vector of 4, comma, and then just the label, 0, okay, as an item, not vectorized. This is pretty important. So now that you have this, you've created the train set as you need it, and this can easily be loaded into the data loader. And that's the beauty of this, is now you'll be able to access this data through the data loader, and you'll have several features that you don't have to implement manually. Okay, so let's repeat this for the test set now. This test set is going to be the exact same thing, but for the test data. So notice here for I in range X test shape, so that's like 30, and then we grab each vector of 4 from the test set and the corresponding label. All right, so I've created both. Okay, so now, we've already looked at them. I can show you just 3 so that it's more obvious. From the train set, you can see I have 4, a list. From the list, I have 3 samples, essentially in tuple format. All right, and here we go now. We start to use the machinery of Torch, right? And one of the first things is from torch.utils.data.dataloader, and we're just going to load our data and create our train DL, our train data loader. And you will see that this approach is very consistent throughout. When you're using Torch, you should always use the data loader. So notice here this is for the train set, so I'm going to give it iris train list. But notice that I have these 2 very nice features actually that before you had to implement in code, now you don't. Here, all you have to do is specify the batch size. So for instance, 16. So what does this do? Essentially, whenever you're grabbing from this data, you're going to grab in batches of 16. So you grab 16, then 16, then 16. So every time you grab something from here, it'll be a batch of 16. Do you guys see that? And all you have to do is specify this parameter to be batch size equal 16. Also, we have this term here, shuffle. This is actually really important. So what this means is that the tuples are being randomized. Every time that you start like a new running through all the batches, the data is being randomized. This is important, all right? So remember that when you train a model, you show it all the data multiple times. But let's say you have 100 samples and you have 1,000 epochs, right? So every epoch you would show 100 samples to the model to learn in batches of 10 or 16. Well, one nice thing to have is every epoch you want to shuffle. You want to shuffle the batches. That's the key thing, right? So and that, believe it or not, helps the model to learn. So this is one feature that you want to have and take advantage of. So here, now I've created my train DL and it is ready to be used, okay? So that's ready to be used. Now the next step then is so I have, for the test size. So here for the test size, notice that instead of creating, since I only have 30 samples, right, I'm not going to give it batches of 5 to have 6 of them, right? Instead, I'm just going to say that the whole batch is 30. That way, all I have to do is give all 30 test samples to the model. Does this make sense, guys? So notice here, all I'm going to do is I'm going to grab from X, so X test shape 0. So I create a variable. If I print that one, it should be 30. 30, right? And instead of specifying a batch size of 16, I'm just going to plug in that value. This is a common mistake I see students make when they're evaluating their homework. They forget about this. Their test set maybe has 1,000 samples or 10,000 samples, but they're using batches of 64, and they only run it once. So what does that mean? It means you only evaluated on 64 samples, okay? So make sure for the test set, do something like this, right? So that you evaluate all the samples, okay? So notice here, I'm going to use the same idea, but for the test data, right? So I'm calling torch utils data loader. I'm giving it now iris test list. And notice here, instead of using batch size of 16, because this is just for testing, you remember testing is not the same as training. Training is GPU intensive, repetitions, thousands of epochs. right? So it's gonna, if you want to go out on a Saturday, right? So, training is going to take a long time. But testing, no, right? So that's done only once. So you don't need to have batches here necessarily. Instead, we just say there's 30 test samples, and that's it. Okay? Got it? Any questions? All right, so this is actually really nice. Like, I can tell you guys before, even 3-4 years ago, this was not available. And you had to do all of this from scratch. You had to do the randomization, the batching. It was, your workload was heavy. Okay, now, as long as you put the data, you want to take advantage of this benefit. Put the data in the correct format, load it into these data loaders, and it makes all the coding so much easier, and it's very well developed so that it's amazing how this idea scales so well to everything, so that you could be training ChatGPT and you would still be using the same thing. Okay? All right, so we have our data loaders. As you can see, this is a PyTorch specific thing. And if I print one of these, notice that now it becomes more of an object related to PyTorch. So you can see it's a data loader object. It's serialized, what is called, which is essentially, consider the fact that CUDA is the library that runs the GPUs for machine learning. That's a C++ library, okay, because it has to be very fast, right? It's very close to the hardware. So PyTorch also knows that, even though we're writing Python right now, this eventually will run on CUDA in C, right? So essentially when they built PyTorch, you can think of Python as an interface to C, okay? But you don't have to code in C. You still code in Python, and then as you create the computational graph, you start to use these things that are serialized, essentially as if they were like C code that has been made executable. Do you guys see that? And that just makes it run super fast. The whole point of this is fast, and believe me, when you get to phase 2 of this project, you'll suffer a little bit through the fact that it takes so much time and it's so big, and you'll get frustrated because it's training and it breaks because you should have used batches of 16 instead of batches of 32. You see that? So you'll have to go through all those ideas. All right, good. So I believe that's everything with the data. And as you can see, the next thing that's coming is the neural network. So we're going to build our very first neural network in PyTorch, okay? One of the things, the last algorithm that we will cover from scratch is something called a residual network. But also here, you'll start to bring in, actual transfer learning based models, to bring in more power. But before we get to that, let's just build something very basic, okay? And this is going to be the pipeline that you need to master. It is an object-oriented pipeline. So what you can see here is it's a class, right? So every neural network that we create going forward is going to be some kind of a class, okay? So that's what I'm going to discuss now. It's very consistent, but we just have to learn the basic ideas. You can see I actually have here one neural net and a second neural net, right, as for contrast. So I'm going to start with this one that I have highlighted blue, okay? And this is going to be the, you guys have already used this, right? This is the multi-layer perceptron that you had available in Weka. I believe in sklearn we also saw this a little bit. Here, we're going to implement it from scratch. And you have to understand these ideas, okay? So I'm going to show you I'm going to start like this. Let me just copy this, plug this in here. So we're going to have a basic approach that we're going to take, okay? Whenever we build a neural network, we have a class here which will have two functions. Okay, it'll have one function called the init class, which you guys, when you took your programming, right, object-oriented, you learn about constructors, right? So I'm sure you learn about the constructor. That's what this is, the init class, right? This is where you initialize variables and all of that. And then the neural network will have a second function called the forward function. Okay, notice I'm doing that here. Do you guys see that? This is key, but also very consistent. Every neural network will have these elements, okay? And so you just fill in this area and this area with the details of the architecture. Got it? And so that's going to be really nice. If you were building ChatGPT, believe it or not, you would build it exactly like this. In fact, this is designed because as the network becomes bigger and bigger, it's very difficult to like keep track of everything that's going on. So object-oriented programming helps out a lot in that regard. So notice here, right? So every neural net is going to be a class. So notice here, that's the class. I'm going to give it any name I want, so I'm calling it here MLPNet. An MLPNet has a definition. Has a one input layer, one hidden layer, one output layer. So we're going to see what that means in a second. Notice that it uses class inheritance, so that means we provide something here. What do we provide? nn.module. What is nn.module? Is the thing that we brought in from the library up here. nn. Right? So from Torch, we're bringing nn, and that's the object that allows us to define any neural network. Do you guys see that? So a little bit of class inheritance. But that's it's like I can literally put numbers on the things that we have. So 1, it's a class. 2, you give it a name. 3, it always inherits nn module. Do you see that? 4, it always has an init class. 5, it always has a forward class with those specific names. Now, could we have more functions in here? Sure, you could add your own functions. And maybe later we'll see an example where we need to add our own function. But the default is to have these two to define a neural network. Okay? So the init class is just def. These are 2 underscores, right? That's how you do it in Python. So 2 underscores, init, 2 underscores. All right? So this gives me the init class. Remember that you have this idea of self, right? That you have to have when you're building classes in Python. And then here you pass any parameters that you want, like x means, x deviations. Do you guys remember? I calculated these, right? A little bit ago, these were the means and the standard deviations of my data. So once I get my x inside my neural net, I can just do the standardization in there. Why do I do it there? You could do it outside, totally, but then what if you decide to deploy this to a website? Then you would have to also do that standardization outside, right? And so that makes, they have to add more code, or you can just do it inside the network and then deploy that standardization, that's already included in the model. And so you can just deploy it. It makes it more easy to do. So that's it, right? So we have our init function here. And then here, that's where we define all of our variables, etc., as I will do in a second. And then once I define all my variables, I need to build the architecture. Okay, so x comes in, and then this happens, and that happens, and this happens, right, until I get to an output. So the architecture of the neural network is going to be done inside the forward function. Do you guys see that? So that's it. All right, obviously we'll do many examples of this where this becomes obvious, but this is the overall architecture. Okay? So notice here I'm going to pass, when I create in the constructor, when I create the class mlp.net, I'm going to pass x means and x deviations. All right, then here also, now we can get into some of the details, right? So I'm going to define several things. Okay, So here I'm going to define, remember that whenever you have a class, you use self to say, okay, this variable belongs to this class, right? So here I'm passing x means and x deviations, but I want to load these variables into the class itself, into its internal field. So that's pretty easy, right? Pretty straightforward, just so that you can reference it throughout later. Okay. Then I'm going to need to define, I'm going to need this new thing, NN linear. What is NN linear? Well, NN linear, if you notice, all semester we've been talking about a line equation, right? Can anyone tell me what that line equation looked like? What was it? W times x plus b, right? W times x plus b. Do you guys remember that? We've been doing that all semester. We talked about the perceptron. That's the essential equation of a neural network, right? So as it turns out, you could do this, right? But as you start building a lot of neural nets, you have to then declare W1, W2, W3. So create a whole bunch of W variables, a whole bunch of B variables, and it just starts to become pretty massive. So at some point, the people that developed Torch decided, okay, let's be more efficient here. So they created this thing called NN linear. NN linear is essentially holding this equation inside. But what's really nice about it is that instead of you having to define all the variables, the second you create an NN linear with some values here, it creates these variables of W and B inside for you automatically. Do you guys see that? So, you know, something that would have taken maybe 5 lines of code for you to define now is just 1 line of code, and a lot of it is abstracted. This is a very common theme, by the way, in machine learning today, abstraction. Yes, we could have written this with the variables, but it just makes for the code, you know, it makes it more complicated to read. So people just create a wrapper, what is called code wrapping, right? And it's an abstraction, which, you know, you guys are familiar. It's like another class, right? So what is it really? Object-oriented programming. There's a class called linear that has an X and a W and all that stuff. Does this make sense, guys? This is a pretty important concept to understand. I like to ask questions about this on the exam. All right, so write it down, you know, NN.linear equals this W X plus B, right? Just write that down. And we'll come back to this idea later, but it's very important that you understand, okay? So I feel that students, if they don't make this connection, they don't connect back to the math, right? They won't connect back to the idea that it is still W times X plus B. That hasn't changed at all. It's just that the abstraction makes the coding easier, for sure, as this is deep learning, so you're going to have lots and lots of layers. All right, so hopefully that made sense. So I did self, and I need indentation here. Now you need to give these names. So for instance, I'm going to call it linear 1. So that's the first layer, the second layer, the third layer. Okay? Usually the values that go here have to do with the number of neurons that you're going to have in the previous layer and in that current layer. All right? So essentially it's something like this. If we go back to this idea of H1 equal W times X plus B, something like that, right? So what this essentially means is that your X values are vectors of size 4. That's why this is 4. Do you see that? And then the vector that comes out, H1 then, would be a vector of what size? Logically speaking, if you look at this, if 1 is 4, 3, right? So it comes out as 3. Do you guys understand? So a vector of 4, like iris, goes in, and then a vector of 3 comes out in the next layer. All right? So that's essentially what the neural network, what you're defining in the neural network. So another way of looking at this is, if we go to the whiteboard, let's go to the whiteboard. All right, so 4 and 3, right? So we define a linear layer. So that means as a neural network, this is x, 4. The next layer, so we have an nn dot linear, that is, was it 4 comma 3. So that just implies that the next layer, not the last layer, but the next one, H1, is 3. Do you guys see that? How do we do this? Well, this is a math operation. Remember that here we have what? Connections, right? That are usually referred to as weights. Do you guys see that? We'll come back to this operation a little bit later, but I want to finish the PyTorch first. But this is just a matrix multiplication. So if you look, there's an x, there's a w, and there's an h1, right? So that just means h1 equals w, that w, which is these, matrix multiplication x, plus the bias, which is essentially for each one of these, you have a plus its corresponding, the bias. Do you guys see that? So that's, when I do this nn linear for 3, all of this is implied. And it's done internally by the construct. It defines some biases, we don't even see it. It defines these w's, we don't even see it, although they do live there. We can extract them if we want to, okay? And then the x comes in and it becomes transformed into a layer h1, okay? The next layer will mean then, now I'll just change color. Well, I'll erase these just for simplicity. Change color to, oops, put a pencil. The next layer will probably be nn.linear, right? Let's think it through. I need to define this layer, right? I haven't connected it, but I need to define it. I want the next layer to be 2 for whatever reason. It's not the last layer, it's just another layer. So again, I'm going to have a whole bunch of connections. Right? I'm going to call this W. Remember, this is a different one, so let's just call it 2 or something like that. They're different. So what do I have now? I have an H1, a W2, and an H2. So to produce this H2, what do? Not X anymore, because X has been transformed into H1. So it's H1, right? Matrix multiplication, W2, these weights, plus its own corresponding bias. And you can see this is the next layer, right? So this was the first layer that came from X, but this is the next layer that comes from H1, the one I just created. Do you guys see that? So this has 2. So when I'm defining this red area, all I do is nn linear. However, I have to define these values. Okay? So what do you guys think? What are those numbers? Look at the architecture in green here, right? For that, all we had to do is nn linear for 3. Do you see that? So now I have to do, for this red, nn linear, what are these values here?
3, 2.
Yes, very good. Perfect. Thank you. Exactly. 3, 2. That's all you need to understand. That's it. All right? So, if we go back to the perceptron code, I'll make you code this, completely, or if we do this in NumPy, I will make you create a W and a B and all that. But PyTorch is meant to help you. It's got this construct. And you just have to understand that the underlying thing looks like that. But you just declare these 4, 3, 3, 2, and so on. All right, they're still unconnected here, right? So I'm still just creating these but I will need to connect them, and they're connected, the green and the red are connected in the forward function. So I define them in the constructor, in the init function, and then I connect them in the forward function. That's it. All right, so let's see this through then to the end. So hopefully this was helpful. Let's switch over to the share the screen. Okay. All right, so now we can add, I think, everything, because you understand the basic underlying concept. So I'm just going to add all of these. All right, so this one's repeated, so I can just, I think, yeah, get rid of one of these. So notice I have, whoops, I'm going to have here linear 1, ignore the activations for now, and I'm going to have linear 2. Notice that this one is 3, 3. Why 3, 3? Because actually the other example was just for an additional hidden layer. This is specific to iris. Okay? So this is going to be 3, 3. We'll see this in a second. And then I have these other functions that are going to be applied. So sigmoid, activation 1, softmax, activation 2. And we can disregard the dropout for now. So now let's look at this architecture in the whiteboard now that you understand. So notice 4, 3, 3, 3, but we also have these things called activation 1, a sigmoid, activation 2, a softmax. Okay? So let's switch to the whiteboard. Okay, let's see if we can fit here, right? So I'm going to switch color. I don't need to do the math part anymore. I'm just going to do the network part. So 4, 3, that was the same. So 3, 4, and these are connected. I'm just going to connect it a little bit. But in the second, linear 2, it's 3, 3, not 3, 2. So that means 1, 2, 3. Why is it like this? Because it's an MLP. A multi-layer perceptron only has one hidden layer. It has an input layer, one hidden layer, and the last layer is the output layer. What does this correspond to here? The classes. Setosa, Virginica, or versicolor. Do you guys see that? So this is Setosa, Virginica, versicolor. That's why we have 3. Because it's going to learn to predict which one of these classes is the most likely. For instance, it's going to say, oh, I think it's 0.98, 0.01, 0.01. Do you guys see that? So what's the highest class? 0.98. What is it? Virginica. Make sense? That's what it's going to learn. So that's why that we did here, it's linear, and in linear, 3, 3. Why? This has 3 and this has 3. Do you see that? That's essentially how it works. And then what about these activations 1 and 2? Well, activation 1 applied to the linear 1. So let me use a different color here. So activation 1, once these values are computed, they need to go through that function. And it's going to further modify them. Remember the step function where we had a value, if it was greater than 0, it was a +1. If it was less than 0, it was a -1. That was the step function from the perceptron. It's the same thing. Only a much more advanced function, a sigmoid function, in fact, that we can discuss later. What about the softmax? That one will apply to linear 2. So here, the softmax. And it's similar. That actually, softmax is pretty important. I will come back to that concept later, what it means. Essentially, it makes all values add up to 1, amazingly. We'll see that, and it's a very simple equation. And that actually is important, because what if these values were like 0.3, 0.8, 0.4? It's still going to select 0.8, right? You see that? It's still going to select 0.8. But this is not a true probability distribution, because a true probability distribution should add up to 1. And our classes, as we will describe later, do add up to 1. So because they're basically binary, it'll be 0, 1, 0. So it always adds up to 1. So when we apply the softmax, we can have values like this, but it'll convert them to something like this, which adds up to 1. This will add up to 1, just like our labels, our real labels, will also add up to 1. So we'll see this later. Does that make sense, guys? So the things that I'm defining are the connections, and then the functions. Activation 1, activation 2. All right, so I think that describes pretty much everything. So we can now go back to the share screen. All right, so you can see I define linear 1, 4 to 3, linear 2, 3 to 3, and I'm going to use these activations whenever I need them. So now that that's done, all of those things are declared, but they're not connected. I need to connect them now, and I will do that in the forward function. So it's going to be done through this. So if you notice, the forward function is the one that will have the data. So the x that goes in, right? So x times w plus b. So that first x comes in. The first thing that you do with that x, because it's not standardized or scaled, is you want to scale it. If you remember, I said you just take the data x minus the means divided by the deviations that we just calculated, right? Once that's done, that x goes into linear 1. Do you see that? What is linear 1? This one over here. So this vector needs to be of size 4, right? So that is essential. So this is 4 because it needs to fit in here, which is size 4. Can't be greater or less. It has to fit perfectly, the tensor. So it goes into 4, and guess what? It gets transformed into this. Now it's size 3. Do you see that? In the next, imagine you're in that network, right? We had 4, then 3, then 3. So it is now 3. Okay? So then what happens? That 3, that vector of 3, goes into activation 1. That's that sigmoid. Modifies the values further to produce this x. And then that x now goes into linear 2. The vectors are of size 3, and it goes from 3 to 3. Do you see that, guys? And then finally, this x then goes into activation 2, which is that softmax, to produce the final prediction. And that's it. That's your prediction of for the classes, like I showed, 0.01, 0.98, 0.01. That's it. That's a neural network. Any questions? All right, so hopefully, so right now focus more on understanding the overall construction. We will dive in as time permits a little bit more into these ideas, but you just built a neural network, a multi-layer perceptron, in fact, in Torch. All right, so there it is. So now we have time. Let's run it, and let's train our first neural net. Okay. So I'll skip this part for today. We'll come back to this one on Wednesday. Right. This will be a deeper neural network, and once again, I'll create the whole graph. Here's the training loop. Okay, so we want to take a look at this one. Now this one is very easy because we've done everything like creating the train DL and everything before. This code could be very long and very confusing, but now it should be pretty straightforward. And always, what's amazing to me is like I've looked at the training loop for something like a ChatGPT, and it's the exact same one. So it works exactly the same. So let's take a look, right? So we define a function, train loop. It's got the number of epochs. We pass the model. We pass something called the loss function, which we need to define. We'll see what that is in a second, and the optimizer. So notice that it's got two for loops. The first for loop is we're just going to show all the data and epochs, right? So let's say that's 4,000. So we're going to repeat this process 4,000 times. Then after that, look at this. We're going to use in the second for loop, we start grabbing the data from train DL. But because we did all that processing, now we can grab XB, YB. So we're essentially grabbing batches of 16. Do you see this? So you should already know the dimension of XB. It should be what? 16, 4. Every time, it's almost like, you remember those old trains where you would take a shovel and grab like the coal and so that's what you're doing. You're shoving 16 into the model, 16 into the model, 16 into the model. So XB is a tensor that is 16, 4. And YB is a tensor that is what? 16, 1. Do you guys see that? So that's what it is. Once you have your XB, notice it goes into the model itself. So you're going to send a tensor that is 16, 4 into the model. And the model will produce something that is 16, 3. Right? The Y-pred will be 16, 3 because it's 16 predictions, but it's predicting in vectors of 3. Do you guys see that? Y vectors of 3 because we define that to be 3. You see that? All right. So I have my Y-pred. Right? And then that's why I have these print statements here, because you can print out the shapes of them. And we can do this next week. Oh, sorry, on Wednesday. I just want to finish this one today. Now notice loss FN is the thing that will compare the predicted to the real. Do you guys see that? So essentially, we've grabbed the real data from here, and we've got the predicted data once this XB goes into the model. So if the weights are bad, you can expect the Y-pred to be bad. But once the weights are good, it means it's learned, right? So the XB starts to produce Y-preds that should look a lot like YBs. Now keep one thing in mind. This one is 16, 3. This one is 16, 1. So there's the same data, but they're inconsistent. But that's actually not a problem because the loss FN that we use knows that this is a common issue, and so it can handle it for us, right? So here the YBs will just contain the actual label like 0, 1, and 2. All right, and then once you have this loss that you've created, right, essentially it's like this has combined all the data and operations, and it's all linked. Then you just do these 3 little commands essentially here. All right, and this is the training part. So here, this one's 0 grad, you can almost ignore. There's an accumulator variable in there, and you're clearing it every time. This one, and we need to dive more deeply into this, but this essentially, for now, let's just say performs the derivatives. Okay, this does the calculation of the gradients, right? And it essentially tells you if you're going to, when you're going to update the weights, you want to know if you're going to add or subtract. Do you see that, guys? That's essentially what this does. This whole thing is massive, okay? So this, even though it's only one line of code in Torch, it's like, it's like a massive apparatus that allows us to take the neural network, have it as a graph, send data forward, compare to the real, calculate the error, back propagate. It's a whole process that we will discuss later, but just think of Torch as doing this for us with this one tiny step. So here it calculates whether we're adding or subtracting, and then here we actually update the weights. You see that? So essentially we have here, similar to the perceptron, we have W equal W plus, and then we need to know, okay, we have a learning rate times, we need to know the sign, and the sign is obtained by this step. Do you guys see that? There's a value involved, but the key thing is this step figures out this idea of the sign. So then let's say it says, oh, okay, it's negative. All right, -1. Do you see that? And then now you know, in this LR, we define that as 0.001. And so what are we doing essentially? We're decreasing, right? The W. Our current W is going to be decreased by a little bit. And another time, the sign comes out to positive. Oops. So guess what? Now W goes up. Do you see that? We're adding a little bit to it. So these two steps are doing this, but there's quite a little, there's more going on there. And that's it. So once we create this, we have our training loop, and we're almost done. Let's just see this to the end. So the training loop is done. All we have to do now, if you notice, is actually do the training. So here we call all the functions. So notice here I'm going to call mlp.net, so I'm instantiating the class. I provide x means and x deviations. I need to initialize this thing called torch optim atom, and I'm going to call it OPT. Notice that you're going to link this model to this optimizer. You can see the name model here. And what we link is the actual parameters. So we're saying you need to update the weights and the biases of model. Do you see that? So that's what it's doing. And notice this is where we define the learning rate, which is this thing here. So it's invisible here, right? But it's you actually define it here. Okay? And then finally, this loss Fn that I use here is a function we have to understand called cross entropy. So essentially it takes two values and it does some math to figure out a value. Okay? And once you have that, all these parameters, n epochs, model, loss Fn, and opt, are added to the model. And there you go. And as you can see, it is now training. This is training the model. What are desirable things? You want this value called the loss value to go down. That means that the model is learning. Okay, that's really, so notice it started at 1.11, starts to settle around 0.55 something. Do you guys see that? So it's running, and so we just let it run until it finishes. You can see this was just Iris, right? And it took a little bit. So this is where you start to see, I should have, I wish I had a GPU, right, as you have this. It finished here, so you can see we've got a green check. So at this point, the model is trained on the train data. Do you guys see that? And so just real quick, let's see here. Yeah. So this is familiar to you guys, right? So this is the same function we've used before, print stats metrics. I'll just use it. And I'll explain this in the next class, but I'll just show you that at the end of the day, it's the same metrics that we've been using. So here, of course, I'm going to use the model, the trained model, but I'm going to evaluate it on the test set. And then you can see I get my familiar performance metrics. From this, you guys know what? What does this tell you about this model? Is it bad? Terrible? It's good, right? It's a good model, right? It's a 90% F measure, good confusion matrix. And there you have it. Same thing you did at the week 1, right? Or week 2, whatever it is, you're still doing it now. Only now you have way more power with PyTorch. You've only created a very basic one. All right? All right, guys? So this is a good stopping point. On Wednesday, we'll pick up here, add a deeper neural network. So we'll do DL and explain a lot of the things. And after, it just starts to get repetitive. We just add a little bit here and there, and so on. All right? So I'll stop here, and I'll see you guys on Wednesday.